Hello, welcome back to Cinderella Math. Today I'll be doing a somewhat short, I think, video on remainder theorem. This is typically a pre-calculus topic, though you could maybe see it in an advanced algebra 2. And it's really quite easy. Here's the kind of the formula. I'm not going to give like a full formal definition, but it's just another way to evaluate a function at a certain value. We're going to call the value a, and that's actually equal to the remainder of that function at a. So this is going to be using synthetic division. I do have another video with synthetic division and long division. If you look up on my channel, Dividing Polynomials, you can see that in more detail. But for today, I'm just going to assume you already know synthetic, or if you don't, go ahead and watch that other video on dividing polynomials. And we're going to use this remainder theorem to evaluate some functions. So I have a couple examples here. Example 1. We're going to have a function f of x is 4x cubed minus 13x plus 10. And our first question here is to please find f of 1. Now we could just plug 1 in there, and it's not that bad. So let's actually do that. So that would be 4 times 1 cubed minus 13 times 1 plus 10. So that's 4 minus 13 plus 10. Negative 9 plus 10 is 1. So that wasn't that bad, pretty easy to compute. Let's go ahead and do it with the remainder theorem and see if we get the same thing. So we take the value that we're doing, known as a, and that's going to go into synthetic. So we're going to put 1 in the box, or like I like to call it the timeout box. And now the coefficients. Now careful, we have 4x cubed. We have 0x squares. We do need that 0. If you don't put that placeholder 0, it won't work out right. And we're going to drop down, multiply, put it in the next available column, and add straight down. Multiply, add straight down, multiply, add straight down, and this last number is your remainder. So we have just shown that this does indeed work. F of 1 is the same as the remainder at 1. Okay. Let's use that same function and do a few more. So part B, same example, same function, is to do f of negative 2. So again, we could just plug that in. It wouldn't be that bad, but it would be a little more annoying than the previous one because of the negative and all that good stuff. But let's just run it through synthetic. So we're going to put in negative 2 into that box. And we have 4. Don't forget about the 0, holding that place of the x squares. Let's drop down, multiply, add, multiply, add, multiply, add. So we can say that f of negative 2 is 4. Okay, these next two examples are where I really think the remainder theorem kind of shines. Oh, so sorry, next two problems. Same example, part C. They want to know f of a half. Now you could do that, but I don't want to cube 1/2. It's doable for sure. I just don't want to. So this is where I think synthetic does rule the day here. So we'll put 1/2. 4, don't forget the 0. Drop down. Half of 4 is 2 and add. Half of 2 is 1 and add. Half of 12 is 5. Oh, nope, 6. Oops, that's negative 12. So negative 6. There we go. 4. Boom. That, to me, is faster and easier than popping in 1/2 here and here. It's doable, but it would be some ugly fractions. So why not avoid those if we can? Okay. And then the last one here, same example, last part of this example. Part D, they want to know f of 8. Again, we could cube 8, but it's big. So if I can avoid that, I will. So let's put 8. And we'll drop down, multiply, add 8 times 32. Of course, it depends on how uptight your teacher is if you want a calculator or not, but this is easy enough to do off to the side. 256 minus 13. Well, we're adding, but adding a negative, we're really subtracting. So we get minus 13, 243. 243 times 8. Again, if your teacher's not uptight about calculator use, you totally could just use a calculator. And then we'll put that there. And we get 1954. So a little more annoying, but I still think that was better than having to cube 8 and then times that by 4 and all that jazz. So this isn't perfect. It still can definitely be annoying, but I think it was a little bit easier than just straight up direct substituting 8 into the function. So f of 8 is 1954. Okay, that was example 1. I'm just going to do a few more and then you probably get it by then. It's pretty straightforward here. All right. We have a new function, f of x. So this is example 2. New function f of x is x to the 6th minus 4x to the 4th plus 3x squared plus 2. And I'm going to go ahead and just put all the questions up. A, we want f of 2. B, f of negative 4. C, f of 3. Okay. All right, so we're going to just do straight up the remainder theorem. We're not going to do the direct plug, though you could, but I don't want to have to take 2 to the 6th power and 2 to the 4th power, even though it's not that bad and it certainly is doable. I just don't want to. So I think this will be easier and in the long run, probably faster. So for question A, we'll put 2 in the timeout box. We have a 1 here. We have no x fifths to the 5th, then a negative 4, no x cubes, then a 3, no just plain x's, and then a 2. So we are placeholding there. Okay, and if you need to write it in, we have 0 x fifths, 0 x cubes, and 0 x. That's where we're placeholding. And now we drop down, multiply, add, multiply, add, and then just keep on going. And I got 14. That would be so much faster in the long run than doing 2 to the 6th minus 4 times 2 cubed and so forth and so on. That'll just be the quickest way to get the job done there. Okay. Let's do f of negative 4. So I'm just going to delete the second part here. Let's change the timeout box to be negative 4. And now this would really be a pain to do direct substitution. Negative 4 to the 6th, I mean, doable. I just don't want to do it. Especially if you have a teacher or a professor that is really uptight with calculator use and they want everything done by hand. There are some of those teachers still out there. That would be a pain. It just would be. This is going to be much easier. I've already got all my placeholder zeros in place and we're ready to drop down, multiply, add straight down, multiply, add straight down, multiply, add straight down. Now this is getting a little annoying. Negative 48 times negative 4 would be positive something. 192 plus 3, so that's 195 multiply, so 195 times 4, 780 negative. I'm going to run out of room right here. So this right here is negative 780 multiply times 4, positive 3120 plus 2 gives us a final answer of 3122. I mean, still a little annoying, but way better than having to take negative 4 to the 6th. That would just not be fun. With a calculator, it's not that bad. But again, you might have a teacher that doesn't allow calculator or wants to see the whole work with the remainder theorem. So that should be f of negative 4. Yep. And we have one more here. So this was 3122. I'll clear off. And now let's do f of 3. Again, you could just pop in, but I don't know what 3 to the 6th is, and I don't want to spend the time figuring it out. So we'll just put 3 in the timeout box, write down our coefficients, including those ghost zeros. And now we're ready to drop down, multiply, add, multiply, add, multiply, add, multiply, getting a little big here, add 48 times 3, 144. Add 144 times 3. Add 434. And there we go. That should be the function at 3. Yep. Okay, I've got one more for you. Let me grab it. Example 3. F of x is 3x cubed plus 5x squared minus 10x plus 1. So no invisible zeros here, right? It goes 3, 2, 1, constant. So that's nice. We don't have to place hold. And we want f of 3, f of a third, f of negative 2, and f of negative 5. So we'll just go straight down here, starting with 3. Again, we could plug that in. It wouldn't be awful, but this is going to be quicker. Taking my coefficients, dropping down, multiply, add, multiply, add, multiply, add. Done. It's always the last number is your remainder. And now let's do a third. This is where it really comes in handy with these fractions, because I do not want to do 1/3 cubed and 1/3 squared. Though we could, I definitely just don't want to. Okay, so we will do 1/3 in the timeout, take our coefficients, drop down. 3 times a third is 1. Add 6 times a third is 2. Add negative 8 times a third would be negative 8/3. So 1 is 3/3, right? 1 whole pizza plus negative 8/3 would be negative 5/3. So still got a little ugly, but not till the end. If we would have just done direct substitution, it would have been ugly from the get-go. And by ugly, I mean just full of fractions that are not super fun to deal with. Okay. And now the other two, Should be pretty straightforward. I'm just going to get that. Now we're coming down to C, f of -2. This wouldn't be that bad direct substitution, but again, I think this is faster. We drop down, multiply, add, multiply, add, multiply, add, and done. Way faster than this direct substitution. Let me just check that one real fast. I think I might have even gone too fast. Ah, that's a negative. Sorry, let me do that one more time. Sometimes I get carried away. All right, multiply, add, multiply, add, multiply. There we go. Sorry about that. I slipped a sign. That is fixed. Let me see if I can get this last one without slipping a sign. Final one here. Let's do f evaluated at -5. Again, doable by direct substitution, but faster, even when you make a mistake. Faster to even do this, make a mistake, and then fix it, I think. Let's see if I don't mess up a sign this time. Drop down, multiply, add, multiply, add, multiply, add. Let's see if that's correct. -199. Yes. And done. That is the remainder theorem. So it kind of looks scary. Um, and sometimes you think a remainder, you're like, oh my gosh, do I have to do long division? Nope. Pure synthetic division here. And really just plug in and chug in. Pretty cool way to figure out function values when you can't use a calculator. So oftentimes we'll just roll that through a calculator, but there are times where we just don't have our calculator on us, or we have a teacher that wants to see the work. And this is oftentimes way faster and simpler mathematically than plugging and chugging. Especially if you look back to question B here, that would be no fun at all to plug and chug into here. Doable, of course, but no fun. So really handy little theorem here when you need to show out the work for function evaluation. I hope that was helpful, and I'll see you again soon. Hope you're having a great day. Bye-bye.